So our next speaker is Theodoros Vlachos from Ioannina, Greece, and he will talk about moduli space of isometric surfaces in space forms.
Thank you. Thank you for the introduction. I would like to thank the organizing committee for giving me the opportunity to talk about this joint work with my colleague, Polymarakis. So I'm going to talk about surfaces that have the same mean curvature in four-dimensional space forms. I will start with a rather basic question in the theory of isometric immersion, which says that given a Riemannian manifold and an isometric immersion into a space form, so the question is this isometric immersion unique? Uniqueness is always understood up to ambient isometries. Yeah? So if it is unique, if this is the case, then the isometric immersion is called rigid. If it is not rigid, then it is always an interesting problem to describe the space of all isometric, non-congruent, of course, isometric immersions of the manifold into our space form. Related to this basic question is, of course, this question, which says that what are the data, what are the sufficient data to determine an isometric immersion up to, of course, ambient isometries. A first answer to this question is provided by the fundamental theorem of isometric immersions, in particular the uniqueness part. And this says that if you have two isometric immersions that have the same second fundamental form and the same normal connection, then they are actually congruent. Having the same second fundamental form and the same normal bundle means that there exists a parallel vector bundle isometry between the normal bundles that preserves the second fundamental form. Then it is natural to ask the following question. What can we say along these lines if we relax the assumptions of the fundamental form? Yeah? In fact, this question was first studied in this paper, which goes back to 1964 by Bonnet. So Bonnet studied this question for surfaces in the three-dimensional Euclidean space. More precisely, he wanted to know to what extent a surface in R3 is determined by the metric and the mean curvature, just the trace of the second fundamental form. This problem has been studied by several people, among them Bonnet himself, Cartan, CERN, and several others. So what is known about, I will first review what is known about this problem. So there is a local theory, which basically says that generically, a surface is determined by the metric and the mean curvature. There are exceptions, and the exceptions are the so-called Bonnet surfaces. So what is a Bonnet surface? A Bonnet surface is an isometric immersion of a two-dimensional Riemannian manifold in the three-dimensional Euclidean space, for which there exists another isometric immersion that has the same mean curvature. We used to say that this other isometric immersion with F constitute a Bonnet pair. There is a result due to CERN, which describes somehow locally the Bonnet surfaces, the exceptions to that Bonnet problem. So either they are CMC surfaces with constant mean curvature, or surfaces of non-constant mean curvature that depend on 6 parameters and have the following properties. They are Weigarten surfaces, meaning that there is a relationship between the Gauss curvature and the mean curvature. This conformal metric has Gaussian curvature, which is constant -1. These are the local results, but there are also global results. Lawson and Tribuzzi in 1981 proved that theorem that says that if you have a compact surface in R3 that has non-constant mean curvature, then there are at most two isometric emergence that have the same non-constant mean curvature. So what happens in the case of compact CMC surfaces? There are some results. So the first says that there are finitely many non-congruent isometric emergence with the same constant mean curvature. Recently, Smith and Inalia proved that if you have any surface with constant mean curvature, then the space of all non-congruent isometric to that surface, surfaces with the same mean curvature, is either a finite set or a circle. What is our purpose? Our purpose is to study the same question for surfaces in four-dimensional space forms, any curvature. In other words, we want to see to what extent a surface in a four-dimensional space form is determined by the metric, the mean curvature vector field, and the normal connection. We have to make clear what we mean by saying that the two surfaces have the same mean curvature vector field. Of course, this means that there is a parallel vector band isometry between the normal bundles that preserve the mean curvature vector field. So instead of preserving the whole second fundamental form, we only demand to preserve the trace of the second fundamental form. So that's the problem. We want to, given a surface in a four-dimensional space form, we want to describe the space of all isometric surfaces that have the same mean curvature we have. Let me start with the case where the surface is minimal. In this case, we are able to prove that this space, the moduli space, is either a finite set or a circle. In fact, in the case where this space is a circle, it's a standard thing, that how to obtain the one-parameter family of isometric deformation. So start with a minimal surface with second fundamental form, let's say alpha, that takes values in the normal bundle, of course. For its theta, for its angle theta, consider j theta, which is the rotation of angle theta, and j is the complex structure of the surface. And then consider this tensor, which is actually obtained by rotating the second fundamental form of angle theta. Using the minimality, it turns out that this section is symmetric, and one can easily check that it satisfies the compatibility equations, the Gauss-Kotatz and the Ricci equation, and thus gives rise to a new isometric emergence, which is minimal. So the second fundamental form of the associated family is given in that way. It is worth mentioning that it may happen that this associated family is trivial. Trivial in the sense that the surfaces in the family are congruent. This is the case when the surface is what is called isotropic or superminimal. In particular, in case of the four-dimensional Euclidean space, this just means that the surface is holomorphic. So what is our purpose? Well, we are interested to describe the space of isometric emergence of surfaces that are isometric to a given surface and have the same mean curvature with that surface. And our aim is to show that the answer to this question is related to the behavior of the Gauss map. And indeed, we are going to prove an extension of the Lawson-Tribucci theorem for surfaces in four-dimensional space form. So let me first remind some known facts about the Gauss map of surfaces in R4. So we consider the Grassmannian of the two planes in R4. Every plane corresponds to a bivector, a wedge product of two unit vectors. And of course, we have the splitting of the set of the vector space of two bivectors in this way where lambda 2 plus and lambda minus are the eigenspaces of the hot star operators corresponding to the eigenvalues, of course, 1 and minus 1. So in this way, the Grassmannian can be identified with the product of those two spheres. Then the Gauss map of the surface is, by definition, the map that at its point assigns the tangent plane to the surface. And in fact, using the identification of the Grassmannian with the product of two spheres, one may view the Gauss map as the pair of these maps from the surface into the spheres. So now comes the answer to this problem for surfaces in R3. I started with surfaces in R3 because it is easier to state the result. So what is the answer to this question? So assume that we have a compact surface, yeah, in R4. And assume that none of the components of the Gauss map is harmonic. Then it turns out that there are at most 3, of course, non-congruent surfaces in R4 that are isometric to the given surface F and have the same mean curvature with F. So this result is an extension of Lawson and Tribuzzi. Remember that in this result by Lawson and Tribuzzi, there was an assumption that the mean curvature is not constant. This exactly means that the Gauss map in that case is not harmonic, right? So that assumption is replaced in this theorem for the non-harmonicity of both components of the Gauss map. What about the answer to the non-flat space form? In this case, to state the result, we need to the theory of twistor spaces of space form. So let me remind a few things about this twistor bundle. So you have the 4-dimensional space form. What is the twistor bundle? It's a fiber bundle that has by definition, the property that the fiber is actually the set of all orthogonal, almost complex structure acting on the tangent space. So it is a fiber bundle, of course, denoted by pi, the natural projecture. And it is an O4/U2 fiber bundle. It has two components denoted by Z plus or Z minus, and the corresponding projectors are denoted by, accordingly, pi plus, pi minus. So it is known that there exists a one-parameter family of Riemannian metrics on the twistor bundle that makes the projection submergence, Riemannian submergence. And we have the decomposition of the tangent bundle of the twistor bundle into its horizontal and vertical part. It is also known that there is an almost complex structure on that bundle that makes this triple, the bundle, the metric, and the family of the almost complex structure and the family of the metrics, a Hermitian manifold. So we need the Grassmann bundle of planes of the space form and denote these maps by plus minus tilde, which are defined in the following way. They are maps from the Grassmann bundle into the twistor bundle, defined in the following way. Take a plane tangent to the space form. So what is pi tilde plus or minus is the almost complex structure acting on the tangent space, which corresponds to rotation of pi over 2 on the plane zeta and the rotation of plus or minus pi over 2 on the orthogonal complement of zeta. So the Gauss lift to the Grassmann bundle is by definition the map that assigns to each point of the surface the tangent plane. We also need the notion of the Gauss lift of the surface to the twistor bundle, which is defined just by that composition. This means exactly what is the image of a point under this Gauss lift. take a point P on the surface. So the image is just this complex structure which is defined in that way. It is the rotation on the tangent plane of pi over 2 and the rotation on the normal plane of plus or minus, of angle plus or minus pi over 2. We also need this definition. So we have the Gauss lift of the surface into the Grassmann bundle. The Gauss lift is called vertically harmonic if its tension field has vanishing vertical component with respect to the decomposition I mentioned earlier into the horizontal and vertical subbundles. So now we may state the result for non-flat space form. So you have a surface, a compact surface. We have the Gauss lifts into the Grassmann bundle and assume that none of these lifts is vertically harmonic. Then again, we can prove that there exist at most 3 non-congruent surfaces that have the same mean curvature with F. So we have exactly the same result as in the case of surfaces in our 4, but now we have to consider the Gauss lift into the twistor bundle. In the particular case of the Euclidean space, it turns out that the twistor bundle is just this product. Yeah? The Grassmann bundle is trivial, of course, and this is the Grassmannian. The Gauss lift to the Grassmann bundle is just this pair, where G is the Gauss map of the surface in R4. And the Gauss lift to the twistor bundle is this pair. And it is easy to see that vertical harmonicity is equivalent to the harmonicity of G plus, G minus, I mean the components of the Gauss map as a surface in R4. So if none of the Gauss map is vertically harmonic, we know what we gain information about the moduli space. What happens if both harmonic Gauss lifts are vertically harmonic? In this case, it turns out, using a well-known result due to Ruch and Wild, that the mean curvature vector field is parallel. And surfaces with mean curvature, with parallel mean curvature vector field in 4-dimensional space form are either minimal or CMC surfaces in totally umbilical hypersurfaces of the space form. So, so this case somehow is trivial. So from now we exclude surfaces with parallel mean curvature from our study. Yeah. So the next interesting case is to see what can we say in the case where just one of the Gauss lift is vertically harmonic. So what can we say about the moduli space in this case? The answer, in order to provide the answer to this question, I need the notion of superconformal surfaces, yeah? Which relies to the notion of curvature ellipse. So if you have a surface in a 4-dimensional space form, what the curvature ellipse is. So it is just the image under the second fundamental form of the unit circle on its tangent plane. A surface is called superconformal if the ellipse of curvature is a circle at any point. So assume that we have now a simply connected surface in our space form, and assume also that one of the Gauss lifts into the twistor bundle is vertically harmonic. Then it turns out that our surface allows a one-parameter family of surfaces, yeah, parameterized by the circle, that have the same mean curvature with the given surface. It may happen that this new associate family is trivial. When this happens exactly when the surface is superconformal. Yeah. So triviality of this new associate family is equivalent to the fact that the surface is superconformal. I think that it is worth mentioning that to see how the second fundamental form, of the surfaces in this family is related to the second fundamental form of the original surface. So this is the relation in the case where G plus is vertically harmonic, and this in the case where G minus is vertically harmonic. Notice that there is, the situation is more involved than in the case of the associated family of minimal surfaces. Here are theta denotes the rotation of angle theta in the normal bundle, and this J, of course, is the rotation of angle minus theta over 2 on its tangent plane. Are there any examples of this sort? So are there any surfaces that have the property that one of the two Gauss lifts is vertically harmonic? So there is indeed a variety of this kind of surfaces, and this comes from the class of Lagrangian surfaces. So we are, let's say, in R4, we have a complex structure in R4, denoted there by J tilde, and we have the corresponding Keller form. A surface in R4 is called a Lagrangian if the pullback of the Keller form vanishes. The Maslow form is this one form defined on the surface, and the examples are actually provided by a paper by Castro and Urbano, where they prove the following proposition. You have a Lagrangian surface in R4. The Maslow form is conformal if and only if the plus component of the Gauss map is harmonic. The Maslow form is respectively harmonic if G minus is harmonic. In particular, Castro and Urbano gave a lot of classified, actually, compact Lagrangian surfaces in R4 that have conformal Maslow form. So in that way, we have a variety of examples that have this property. So now comes the answer to the question in that case. So you have a compact surface in a space form for which one of the Gauss lift is vertically harmonic. If the mean curvature vector field is non-parallel, case has been excluded for triviality reasons, then the moduli space of the surface is a disjoint union of two sets, each one being either finite or the circle S1. I would like to mention another result for surfaces. This is only for surfaces in R4, compact surfaces in R4 that are not superconformal. Again, under the assumption that one of the two components of the Gauss map is harmonic, and under an additional topological assumption on the Euler numbers of the normal and the tangent bundle. So in the case where G plus is harmonic, we assume that the Euler numbers satisfy this inequality, and accordingly in the other case. So in this case, we are able to prove that the moduli space is a finite set. So there is no S1 component in the moduli space. It remains to say something about superconformal surfaces. In this case, there is a local result, which is comparable with the result of CERN about surfaces in R3. So it says that there are many superconformal surfaces that allow this kind of deformations. Actually, these depend on 6 parameters. They are Weiergarten surfaces, meaning that the length of the mean curvature vector field and the Gaussian curvature are related by some function. And this conformal metric has now Gaussian curvature equal to -1. In the particular case of compact superconformal surfaces, we show that there is at most one other surface that has the same mean curvature with a given superconformal surface. So I would like to just to give an idea how we approach this problem. So we complexify everything. We consider the tangent bundle, its complexification. We have the usual decomposition into of the complexified tangent bundle into these subbundles, which are actually the subbundles corresponding to the eigenvalues of the complex structure of the surface. We complexify the normal bundle, and according to this decomposition, we split the second fundamental form in its two 0 part, 1 part, and 0 2 part. So the 0 2 part is the Hopf differential, and it is worth mentioning that the following property, that the curvature ellipse at the point is a circle if and only if the Hopf differential is isotropic at that point. We complexify the normal bundle. We decompose the normal bundle in the same way we did in the tangent bundle. In the some bundles, the eigenbundles of the complex structure on the normal bundle. And of course, we have that any vector in the complexified normal bundle is decomposed in that way, where psi prime and psi double prime are the projections in those two components of the complexified normal bundle. Of course, we may decompose the Hopf differential accordingly, and it is an easy property that the Gauss lift is vertically harmonic if and only if the differential, the double prime component of the Hopf differential is holomorphic. Right. So again, I remind the definition of when two surfaces have the same mean curvature. If this is the case, then this pair of surfaces is called the Bonnet pair when the surfaces are not congruent. A fundamental tensor related to our study is this Q tensor, which defined in this way in terms of the Hopf differentials of the two surfaces in the Bonnet pair F1, F2. And what is the meaning? I mean, this Q tensor measures how far the surfaces deviate from being congruent. It follows from the Cotacci equation that this complex differential is actually horomorphic. So we may split it accordingly to the decomposition of the complexified normal bundle in its two Q prime and Q double prime components. Then it turns out that the moduli space can be written as a disjoint union of three components. So M plus minus is this class, is this the surfaces in the moduli space that this Q differential is equal to Q plus or Q minus component. There is no Q minus or Q plus components. And M star is just this subset of the moduli space where both plus and minus components do not vanish. The basic result is this theorem, which says that, of course, for compact surfaces, if one of the Gauss lift, G plus or G minus, is not vertically harmonic, then the plus or minus component of the moduli space contains at most one surface, at most one congruent class. So just to get an idea of the proof, a rough idea, of course, I'm not going to give details, just remind this theorem and show what are the ideas to prove this result. This is about surfaces in R4 that have this additional that satisfy this additional topological assumption. So in this case, we want to prove that the moduli space is a finite set. So what are the ideas? Let's keep this. The ideas goes in the following way. So you have a surface and assume that the G plus component of the Gauss map is harmonic and satisfies this topological assumption. So the first fact is that if you consider the the coordinate functions of the plus component of any surface in that component of the moduli space using the topological assumptions, it turns out that this set is linearly dependent. So we have a set of functions that are linearly dependent. We are also able to prove that these functions are actually eigenfunctions of this elliptic operator corresponding to the 0 eigenvalue. So using standard theory, we have an elliptic operator or a compact Riemannian manifold, yeah, and we know that the eigenspaces are always of finite dimension. What does this mean? This means that if you have a surface that satisfies this assumption and satisfies also the property that the G plus, let's say, component is harmonic, then this part of the moduli space is always finite. Then using the basic theorem, we are able to prove that the moduli space itself is finite. So that's all I wanted to say. Thank you very much for your attention.
Thank you, Theodoros.